Okay, I'm looking at number 24. I've got a double integral over the region R of x plus y, the quantity x plus y, times e to the x squared minus y squared. Here's the region. So they give you 4 lines. X minus y equals 0. You know, just solve for y here. You get y is x. So that's this one right here. Solve this one for y. You get y equals x minus 2. And then that's this one right here. You can do the same for these and you get those 4 lines. You can clearly see the region of integration. Now, it's this problem, they don't give you what the transformation is. And you have to come up with it on your own. So there's a couple of ways you can look at this. You can look at the actual integrand itself and look for things that look obvious to you, like x plus y appears here. Notice x plus y appears here twice. That might be a good substitution. And then if you take the difference of squares here, remember x squared plus y squared, or minus y squared, is the same as x plus y times x minus y. So maybe x minus y would be a good candidate for a substitution or for a transformation. And notice x minus y appears here also. So there's something in the problem that should hopefully lead you to some sort of guess. I'm going to try this transformation. U is x plus y. And I'm going to try v is equal to x minus y. And I'm going to see what happens. So I'm guessing here, kind of. So let's see what happens to these things first. All right. So in this transformation, if I take this equation, all right, x minus y equals 0, what happens to it? Oh, you know what? I have a bigger problem here. I need to first. Well, you know what? Yeah, this will work out perfect. Watch. If x minus y is 0, if x minus y equals 0, then that implies that x minus y must be 0. That implies that v must be 0. If I take the red one over here, x minus y equals 2, that implies that, again, x minus y is v, that v must be 2. If I look at x plus y must be 0, well, that implies x plus y is u, so u must be 0. And if I look at the last one, x plus y must be 3, that implies that u must be 3. And that is a very nice region in the UV plane. So here's u, here's v. So what we have is that v must be 0. Okay, v must be 0s, basically like the v-axis. V must be, sorry. Come on, Robert, get it together. V is 0. Excuse me. Is horizontal. V is 2. There. Why did I draw that in red, green? Things were going well. V is 2. This blue one here was V is 0. Green one, U is 0, which means this one. And then the last one, U is 3. And you can see it's a nice rectangle. I know my U's are between 0 and 3, and my V's are between 0 and 2. That's going to be a nice integral. So now we need our Jacobian. All right, so to get our Jacobian, we need to be a little careful here, because Jacobian is partial of x with respect to u times partial of y with respect to v minus partial of x with respect to v times partial of y with respect to u. But notice these are not solved for u and v. I mean, sorry, for x and y. I do not have yet x is some function I do not have that x is some function of u and v, and I do not have that y is some function of u and v. I don't have that yet. Excuse me, hold on for a second. Okay, I'm dying over here. All right, so let's try and get these to be functions, x be a function of u and v, and y to be a function of u and v. So here's what I'll do. I know that, let's solve this for x. X must be equal to u minus y. So x must be equal to, let's see. Oh, and let's solve this one for y, or for x also. How about that? X equals u plus y, right? So that's correct. Move v plus y, damn it. V plus y. So just move this over. So that's what those two are equal to. So you can say that u minus y must be equal to v plus y, like that, because they're equal to each other. And then move things around, you get u minus v equals 2y, right? Move this y over, v over, and then take 1/2 on both sides like this, and you have an equation for y in terms of u and v. So I've got this one. And then you could do the same thing to get what x is, but even easier, just take this right here. Take x is equal to u minus, now y, you know what y is, right? Y is this, so 1/2 u minus v, distribute, so minus 1/2 u, and then plus 1/2 v. So just distribute through, and then put these two together, you get positive 1/2 u plus 1/2 v is what x is. So you have x as a function of u and v. So let me rewrite that up here. I have that x is equal to 1/2 u plus 1/2 v, and I have that y is equal to this. I'll distribute 1/2 u minus 1/2 v. Now I can come up with the Jacobian determinant. It's going to be partial of x with respect to u, which is this 1/2, times partial of y with respect to v. Partial of y with respect to v is going to be negative 1/2, minus partial of x with respect to v, which is 1/2, and partial of y with respect to u, which is 1/2. And so you get negative 1/4 minus 1/4 is negative 1/2, right? And remember, in the Jacobian determinant, when you plug that in, you have to take the absolute value. So I think I'm ready to transform everything over, get this whole integral over. So we're going to be taking the absolute value of this at the end. Okay, it's the absolute value of that. Okay, so 1/2 is my Jacobian determinant. I'll leave those up there. Okay, here we go. Double integral over the region S. Okay, what was x plus y? X plus y was u. E to the x plus y is u, x minus y is v. So u times v. And then my Jacobian determinant, which was 1/2 with respect to area. And remember that the restrictions on u and v were both constants. So I'm going to go double integral, doesn't matter which way I go. I'm going to go 0 to, I think it was 0, 3. Let me double check. I erased it. 0. Oh no, the restriction on u was, well, I can do it either way, but I was going to do u first. Or the v on the inside, u on the outside. So like that. And then we have the 1/2. I should probably just pull that 1/2 out now. And then u, e to the u times v, dv, du. All right. And now that should be pretty nice to integrate. Just double check here. I've got everything rolling good, yeah. All right. So let's take the antiderivative of this with respect to v first. And remember, u is a constant. So I have 1/2 integral 0 to 3. Antiderivative of this whole thing with respect to v should be e to the u times v. Check it for yourself. Integrating that from v equals 0 to v equals 2, and then du. So just double check. If you take derivative of this, it's itself times derivative of what's up here with respect to v, which is u. So a u pops out, which is this. Now plug in 2 for v. So 1/2 integral 0 to 3. Plug in 2 for v, you get e to the 2u minus, now plug in 0 for v, you get e to the 0, which is 1, so minus 1. I guess I don't need all those parentheses. I can just do e to the 2u minus 1 du. And now integrate that. We have 1/2 times antiderivative of this is 1/2 e to the 2u. Antiderivative of 1 is u. Evaluating that from 0 to 3. And we should be there. Let's see. Plug in 3 first. So I have 1/2. Plug in 3 here, get e to the 6th, half of e to the 6th. Minus, plug in 3 here, 3. That's what I get when I plug in 3. Minus, now let's plug in 0. So 0 in here, I have a 1/2 in front. So 0 in here, e to the 0 is 1, so I get 1/2. And then 0 in here, you get minus 0, so that's it. And so at the end of it all, I get distribute through, I get 1/4 e to the 6th, distribute here, minus 3/2, and then minus 1/4 when you multiply those two together. So you get 1/4 e to the 6th. Let's see, 6, 7, minus 7/4. I guess you could pull a 4th out of there if you wanted to. It's up to you. Yeah, you can pull a 4th out. That's fine, but I'm just going to leave it. All right. That will do it for 12/8.